Hey guys, this video is on enthalpy. First of all, we're going to start with the first law of thermodynamics, and what that says is that energy can be neither created nor destroyed. That's one form of it. But what we can do is convert energy from one form to another. That's one of the useful things that we actually do with chemical reactions. In terms of internal energy, remember, internal energy is the sum of all the energies within a system. Kinetic, potential. The change in internal energy during a process, if that process is a chemical reaction, it's the final internal energy minus the initial internal energy, which will be the total internal energy of the products minus the total internal energy of the reactants. We cannot measure the internal energy directly, but it ends up, as you'll see, we can measure the change in internal energy. And because of the law of conservation of energy, we know that the total change in internal energy has to be zero. And that means that the change in internal energy of the system plus the change in internal energy of the surroundings has to be equal to zero. The idea is that when we perform a chemical reaction, the system would be the chemical reaction, and any energy that's released or absorbed comes from or goes into the surroundings. For example, when you combine phosphorus and chlorine to make phosphorus trichloride, this is an exothermic reaction, and it ends up that 576.14 kilojoules of energy is released to the surroundings for every 2 moles of phosphorus that react with 3 moles of chlorine. Now it ends up that we're going to care whether or not a chemical reaction occurs at constant volume or constant pressure. And we can control, based on our experiment, which of these occurs. So let's look at the decomposition of sodium azide, what they use in automobile airbags to inflate them really quickly. When sodium azide is decomposed, it starts out as a solid, becomes a gas. If we perform that chemical reaction at constant volume, we put it in a container whose volume cannot change, then as that reaction happens and after it has happened, the pressure inside of that container will have increased because now there's more gas pushing out inside of the container. That's why the airbag inflates. And so remember, so in the back of my mind all the time I'm thinking delta U equals Q plus W. The change in internal energy is equal to the amount of thermal energy transferred into or out of the system plus the amount of work done on or by the system. So that means that the energy can go or come from only 2 places, thermal energy and work. And so here, because and remember, we only talk about PV work at this point, pressure volume work, because the volume can't change. None of that energy can go into doing work. So that means that all of that energy goes into thermal energy. Its energy is released. Now, a constant pressure process, same reaction, decomposition of sodium azide. In a constant pressure situation, we have this is a piston basically in here that can move up and down so as to maintain a constant pressure inside of this container. So now when we decompose the sodium azide, we increase the volume because there's the pressure inside here starts to increase. It pushes up against this piston and it rises. The volume increases, and so some of that energy that was released from the decomposition of the sodium azide goes into work. Less of it goes into thermal energy. So you see in these two processes, the energy is distributed. That's produced is distributed differently. Up here at constant volume, all the energy goes into thermal energy, Q only, because delta V is 0. Here, some of the energy goes into thermal energy, and some of it goes into doing work on the surroundings. And so that means that this system down here would heat up less than this system down here, because all the energy goes into heating up the system here. Some of it goes into pushing back against the surroundings, doing work. So are going to talk about QV and QP. QV stands for the thermal energy transferred, the same Q at constant volume, V for volume, and QP, the thermal energy transferred at constant pressure. So remembering that delta U equals Q plus W, let's look at these two situations. If it's constant volume, delta V is 0, what I was just showing you. Because delta U is equal to Q plus W, and remember W is equal to negative P delta V, delta V is 0, this goes away, and the change in internal energy, delta U, of that system is equal to Q sub V. It's best probably to look at it the other way. Because what we measure experimentally is, with a thermometer basically, is we measure Q, the amount of thermal energy transferred into or out of the system. When we measure the amount of thermal energy transferred during a constant volume process, what we are measuring is actually the change in internal energy. So remember, even though it's impossible to calculate, from first principles, the internal energy of a system, just by using a thermometer, we can measure the change in internal energy if it's at constant volume. It's kind of cool. Now, at constant pressure, okay, again, starting with delta U is equal to Q plus W. Now, okay, pressure is constant, volume's not. Remember that piston moving up and down. So delta U is equal to Q plus W. W is minus P delta V. This, remember, we're setting pressure constant here, so this Q will be QP. That's why it's QV over here, because we made the volume be constant, so that's why this is QV. Here it's QP because we're making pressure be constant. And so if we rearrange this equation just a little bit by adding P delta V to both sides, we get what QP is. It's equal to delta U plus P delta V. So it's when we measure the thermal energy transferred at a constant pressure process, it's not just delta U. We're measuring it's equal to delta U plus P delta V. A little bit more complicated. So we take care of that by defining a new function, enthalpy. So this is what enthalpy is, guys. The symbol for enthalpy is H, and it is a state function, which is a beautiful thing. So here's the definition of enthalpy. The 3 lines means it's defined as, it's equivalent to U plus PV. Okay. This is not something we ever can measure directly. We cannot measure the enthalpy of any system. But just like delta U, we can, it ends up, you will see, measure delta H, change in enthalpy. So what I've done here is said that because U is equal to, H is equal to U plus PV, delta H is just equal to delta U plus, well, it would be delta PV, but if pressure is constant, which is what we're defining here, we're making it be constant, pressure doesn't change, so pressure comes out front. Remember that delta just means the change, right? And we know that delta U is Q plus W, and it's QP because we're making pressure be constant. We're saying this is when pressure is constant. QP plus W plus P delta V. But W is minus P delta V, so these cancel. And now we get, this is why we define enthalpy this way. Delta H is equal to Q sub P. In other words, guys, when we measure the thermal energy transferred during a constant pressure process, what we have measured is something called the change in enthalpy. That's why we make the definition. So Q sub P is equal to delta H. Q sub V is delta U. So for a chemical reaction, when we measure delta H, we call that the heat of reaction, delta H of reaction. And this is a really nice thing to have because most of the time in the lab, when we do experiments, it's at constant pressure. It's just open to the atmosphere, so the pressure stays constant, atmospheric pressure. And so that means when we measure the amount of thermal energy transferred during a chemistry experiment, a chemical reaction, we measure Q sub P. What we're measuring is delta H. And so if this is a chemical reaction, what we get by measuring, just by measuring temperatures, we get it's called the heat of reaction, or delta H of reaction. If the heat of reaction is positive, that's an endothermic reaction. If the heat of reaction is negative, that's an exothermic reaction. So the idea is we talk about processes from the point of view of the system. In this case, the system is the chemical reaction. So if you were the chemical reaction and you gained energy, okay, that would be endothermic. So your delta H would be positive. If you lost energy, that's exothermic. You'd be losing energy. Kind of have to be careful because we tend to think about stuff from our point of view and not the system's point of view. From our point of view, it feels like the system is getting colder but it's not. It's really gaining energy, but it's pulling the energy from the surroundings, which is what we feel. Likewise, like in a combustion reaction, which are exothermic reactions, that feels hot to us because the system is releasing energy, it's losing energy. Where does it go into the surroundings? And that's what we feel. A thermochemical equation is just a regular old balanced chemical equation with one other very useful piece of information, the heat of reaction. And it's usually written something like this. It's just tacked on the end there and you're given a number. So for example, the combustion of methane, that's what this reaction here is, the heat of reaction is negative 802.4 kilojoules. Okay, it's a lot of, about half the time I would say you'll see the units written as kilojoules per mole. I personally prefer just kilojoules, and here's why. Because what this number tells you is the change in enthalpy, delta H, when 1 mole of methane reacts with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. It is just another conversion factor, just like the coefficients are in a balanced equation. And so it's, in this case, it's per 1 mole of methane, but it's also per 2 moles of oxygen. So I prefer to write kilojoules, but you'll see it this way too, and either way is acceptable. Another example would be water and carbon dioxide combining to make glucose and oxygen. This is an endothermic reaction because the heat of reaction is positive. And so what this says is that you have to put 2,803 kilojoules into this reaction for every 6 moles of water that react and every 6 moles of carbon dioxide to react to produce 1 mole of glucose. So now we have another conversion factor. We can do a few more calculations. So let's do it. So we want to calculate the change in energy when 2.718 grams of methanol, which is CH3OH, combusts. And you're given the thermochemical equation. It's a balanced equation as well as the heat of reaction. So why don't you guys work this out. Okay, pause the video, work this out, and come on back when you've got an answer. Welcome back. Let's see what we got. So it's what I did is I just converted the grams of methanol to moles. Remember, this number down here is the molar mass of methanol. 1 carbon, 4 hydrogens, 1 oxygen. And I found out how many moles of methanol we had. We weren't told anything about oxygen, so we can assume it's in excess. We don't have to worry about a limiting reactant. And then I just used the heat of reaction as a conversion factor. I have this many moles of methanol. The change in enthalpy is negative 1452 kilojoules per 2 moles of methanol. Watch out for that too, guys. That's the one that people tend to forget. And it comes from right here, because that's what this thermochemical equation tells us, that 1,452 kilojoules of energy are released for every 2 moles of methanol that combust under constant pressure. And so when we multiply this out, we get negative 123.2 kilojoules. The sign's important. It tells us that energy is released to the surroundings. And that's all there is to it, guys.